Okay, so it's really great to have our speaker today, John Jaeger. He is a professor at University of Florida and a sedimentologist. And half of his research life is looking at high latitude sedimentation, Alaska mostly, but I did notice that you worked in the Ross Sea.
Yeah, in Greenland now, and
a long time ago.
yeah, yeah.
But the other half of his research life is here in Florida in coastal oceanography settings.
Yep.
So today John's going to talk about some of the Gulf of Alaska work that he's done with the ocean drilling program. So go for it.
Great, thanks. Yeah, thanks for having me down here. It was a pretty painless drive on down. So thanks for, yeah. There we go. Well, thanks for coming out. I'm going to, as Amelia said, this is one half of my science life. I do a lot of coastal geology here in Florida, so I've got colleagues in the room that I work with on other aspects. But in this case, I'm going to talk to you about some of the work we've been doing for quite a while up in Alaska. But it gets into some big picture climate, global climate, and also its role on how the planet's evolved over the last couple million years. I do want to point out my co-chief scientist, Sean Gulick, as well as all the participants in our expedition, which was 2 summers ago, and as well as some other folks involved. I'll come back to this group. This is a view of Mount St. Elias. Anybody know where Mount St. Elias is or ever heard of Mount St. Elias? Okay. Yeah, it's Alaska, but it's the 3rd highest peak in North America. Most people don't know this because Denali is the tallest, then there's Logan, and then it's St. Elias. And this is a view from the Gulf of Alaska looking onshore. It's 19,000 feet in elevation. It's the steepest topography on the planet, going from the top down to the fjords and icy bay. In front of it is the largest Piedmont glacier, the Malaspina. And this coupled system in here is driven by major tectonic events in the area. But climate's also playing a big role. Oh, that's right, I can do it this way. So this figure is probably pretty familiar to a lot of you. It's a good overview of what global climate has done for the last 70 million years. So when we talk about how global climate changes, we always put it in a perspective that it was pretty warm back in the Paleocene and Eocene. And then what we notice is, and this is just a plot of a sort of global ocean proxy for temperature, but you can see here is sort of a temperature record, that it was warm, and then it's gradually done these step transitions where it's gotten colder and then really colder here since about into the Pliocene and Pleistocene. And it was first argued and this comes out of work in Europe primarily, looking at the Alps and the landscapes, that you realize the force that glaciers have on the landscape. If you've ever been to Yosemite, where I kind of grew up nearby, you just see the amazing force that ice has. And there's a lot of questions to, well, if you remove all this mass from glaciers, it's got to feed back somehow on mountain ranges, just through isostatic compensation. So how much of the landscape that we see on the planet right now is new? And so there was this classic paper written in 1990 by Molnar in England. It was called the chicken and egg hypothesis about global climate. Does climate affect tectonics, or does tectonic affect climate? And that really got a lot of folks thinking. And so the thing that they put in it was that climate, if you change climate to something that's more erosive, it should theoretically lead to an increase in erosion rates, especially in mountain ranges. And so the question that we've been asking, and that we're really focused on, is have surface processes, so erosion, and then transfer the material into the ocean, responded to these climatic transitions? Can we actually document there's been an increase in the amount of material moved from land into the ocean? There's a lot of, you think that would be simple to do, but it actually is kind of tricky. I'll touch on that a little bit. But then if that's the case, if we're taking mass off of land and putting it out in the ocean, what is it actually doing to the land itself from the mountains where this is coming from? And so the area of emphasis time-wise that we're focusing on, I'll go back here, is this period here, the major switch that occurred in through the Pliocene into the Pleistocene. So we get this major global cooling. We do live in an ice house world right now, even though it's a little warm, but it's generally much colder now than it's been for the last 20 million years or so. Most of this is, what you see here is driven by Antarctic behavior. But the thing is that smaller ice sheets like the Cordilleran that I'm going to talk about in the Pacific, also play a role, especially in North America. So the time period that we're really interested in, both in Alaska and other work I'm doing in New Zealand, is looking at this time period called the mid-Pleistocene Transition. So these are sort of a climate summary from the North Pacific. And so this is sort of lower resolution data, and going back into the Miocene 8 million years ago. It was warmer. It's kind of gone up and down. It was relatively warm in the Pliocene, and then it's been cooling ever since until there was a pretty strong cooling event, maybe about a little over 1 million years ago. And from that, what you see here is, more importantly, a transition that's been noted for a long time. And if you look at the amplitude and the frequency of global oxygen isotopic records, they're basically, it's a 41 kiloyear world, low amplitude, high frequency change. So ice sheets are kind of going back and forth, but they're not growing really big. And then all of a sudden, there's this transition from about 1.2 into about 0.7 million years, where now all of a sudden the 100 kiloyear world takes over. There's a lot of debate as to what caused that event, but it is pretty well documented. And so what you see here now is, for at least the last 1 million years, very high amplitude changes in oxygen isotopic values, which correlates probably with ice volume and sea level change, but also that they're longer lived. They're interglacials are 100,000 years apart, and glacials are 100,000 years. So big change. So this should theoretically have an impact on how the ice behaves on land. But our interest is also tying it back into the mountains. And so this was a figure that was put out in 2007 about lots of arrows about how it all links together. So I'll just kind of work you through it if you haven't thought about it from the tectonic side of things. If we start with climate here, it changes precipitation and temperature, which leads to changes in precip and glaciation, which will then influence erosion. You can actually have a feedback, and this is sort of one that Ramo and Rudiman pulled and it came together a few years ago, going back into the Miocene, that if you actually erode material and bury carbon and weather material, you actually can draw CO2 out of the atmosphere, and that might explain sort of the long-term trends that we see. So there's a feedback loop that develops here. But there's also another one here. Erosion influences gravitational stresses in mountain ranges. It reduces the heights of origins. And then tectonics in terms of thickening of mountain ranges, isostatic uplift and deformation, then this feeds back on here because as you move rock up, it weakens it. So it makes it easier to erode through time. Tectonics, of course, if you look at the Himalaya, as you put that up, or Alaska, you then enhanced elevation influences climate because it begins to trap moisture. And Alaska is a good place to look at this. So the idea is that there's a feedback loops that set up and through here. And the one that we're trying to test is this climate influencing tectonics. And you would think mountain ranges have been around forever and they're static. And the main point I'm going to take home, once you take home, is no, they're incredibly dynamic. They can respond on timescales of hundreds of thousands of years, much faster than we ever thought. So that's kind of what we're really trying to get at, is how fast do the mountains respond. So for glacial climates, this is data from Kopis and Montgomery. They looked at erosion around the planet and tried to say, all right, what's the most effective erosion agent on the planet? And it turns out to be Alaskan glaciers. Because they are very large, they're wet-based, as opposed to Antarctica, which is cold-based ice. Because they have a lot of water at the bottom, they can move very quickly, they can remove mass, and so temperate glaciers in Alaska can erode rock at the time scales, at least over modern time scales, of tens to hundreds of millimeters per year. And even over geologic time scales, you're still looking at a millimeter per year of erosion, which is a fair amount when you look at it over 1 million years. So Alaska is the place to go. Let me see how well this works. What's really interesting is this work that we're doing in sort of the empirical world where we go collect the data, at the same time, folks that are working with landscape models coupled with tectonics have made great advancements over the last couple of years with coupled models, ice sheet models with landscape models. And this is a paper that came out in Nature a couple of years ago. And what they did is, I'm going to run you through this animation. It was really insightful in that if you look at a landscape around the planet, in the Pliocene, there were rivers. I mean, basically what you had before glaciers were river systems. And river valleys are V-shaped. And when you put ice onto a V-shaped valley, it has a lot of volume that it can evacuate. But there's a limiting loop that gets caught up in here. And then all of a sudden, when you turn to a 100,000 kiloyear world where you get bigger ice, it has a big impact. And so I'll work you through just to see sort of what the influence of this mid-Pleistocene transition. This is all theoretical work. So what you see here is it's going through this where the ice sheet builds up and then it melts back. And every time it advances down the valley, it excavates a little bit more out. And you see it kind of works its way down. It's always sticking along the ridges here, and this is sort of how cirques form. But at some point, it will end up, after you see here, much of the topography has been eroded in what was a fluvial valley. And now, even though it's going through the same cycle, it's not able to advance down because it's just too low below the snow line. And that's this negative feedback. Now you start to go into bigger 100 kiloyear cycles that are asymmetric. Now the ice really gets to move down valley and begins to erode out a lot more mass. And so just from a theoretical standpoint, you can see sort of there should be this initial pulse of sediment that comes out, and then it drops off, and then it ramps back up again as you go into these very large 100 kiloyear cycles. So we have the ability to actually just numerically to estimate what's going on, and we'd like to try to look at our data in that context. So this is kind of a cartoon that we use a lot for looking at mountain ranges and how tectonics and climate are all linked together. Tectonic processes bring mass into a mountain range. It is then uplifted through faulting action, creates topography that it interacts with the climate. That creates erosion and removes the mass. And so you can see, think of it as sort of it's a cycle that's going on through here. But if you increase the amount of erosion, it should have a change. If you increase or change the climate, it should influence the erosion rates. These are data that kind of show Pleistocene going back into the Cenozoic records of sediment flux from onshore, offshore to look to see if there has been a change in the mass coming off. And this was the first one done by Hay et al. In '88, where they just looked at the thickness of sediment out in the oceans and found that the amount of sediment that dates back to just 5 million years actually is much more than the past. Now, this kind of makes sense because the older sediment's been subducted or accreted, so we've lost it. So that was one of the criticisms of this paper. So in 2001, Zhang and Molnar and others looked not only in the marine record, but onshore as well at basins around the world. And basically, outside of glaciated high latitude, also found it in areas like the Congo, and they found it in basins around Asia. And they argued, in fact, this really did reflect the Pleistocene change in climate influencing erosion rates, creating more erosion and then putting it into the basins. And then the next thing is, okay, so if you take the mass out and you put it in the oceans, what impact does it have on the mountain ranges? And this has been looked at both sort of numerically and conceptually. And the idea here is that as you bring in mass through plates subducting or plates accreting, that mass then moves in a trajectory through the mountain range, comes up, is eroded, and moved off. So you have a accretionary flux and an erosional flux. And if everything's in steady state, the size of the origin, the mountain range, doesn't change. You're adding as much coming in as going out, and conservation of mass. However, if you all of a sudden perturb the system, the size of the mountain range and where all the faulting occurs is going to change itself. And the idea here is, in a paper that Kellen Whipple wrote a few years ago, if you increase the amount of erosion coming out of the mountain, you should see the whole mountain shrink, basically. And the question is how fast. And given the size of the mountains we're looking at, the argument has been that it's about 5 to 10 million years for a mountain range to re-equilibrate to this change. So if you do remove it, how fast? And that's what we're ultimately trying to test. Can we see this influence of climate affecting tectonics? So what we've decided to do is work in Alaska because it's a great place to work to look at this. We've got this amazing ice field that's up here. The highest coastal mountain range on the planet. The sediment is all shunted offshore into the Surveyor fan through a series of submarine channels. And it had some existing work done through the DSDB program back in the 70s. So we had the ability to sort of set up some hypotheses that we could test this. And it really became part of two major programs. If you're going to tackle this, it's expensive, and the logistics here are tough. And so in the late aughts, NSF funded through their Continental Dynamics program an onshore program called STEEP. And that was looking at all of the tectonic effects onshore. At the same time, we submitted a proposal to IODP to drill offshore. And that took, let's see, the first go-through was in 2001. We resubmitted in 6 and drilled in, what was that, 12, 13. Right. So it gives you some general sense of how long this takes. Rightfully so, because, you know, it's expensive to use the drill ship, and they're not going to send it around on science that they don't think is worth it. So the take-home message is we eventually got to drill. We re-drilled a site drilled back in the 70s out here in the distal. We drilled a site close in, and we drilled some sites up here on the shelf. So I'm going to summarize what we found here to give you some general sense of what's happening onshore. So this gives you the perspective of where we are on the planet. For just a quick tectonic take-home message, what's going on here? Why are there mountains? It's an interesting story because you have the Aleutian Trench right here that goes all the way out through the Aleutians. Here's the Pacific Plate subducting under North America. Here are all the volcanoes in Alaska and the Aleutians. And there's a funky thing going on in the corner here. There's a plate, a small plate we call the microplate or the Yakutat block, that was ripped off of British Columbia down here and has been moving up north along a transform fault, just like the San Andreas. It's called the Fairweather Fault. It's made up of basalt and it won't subduct. And so because it's not subducting easily, it's accreting. A big part of what's on the block is accreting, but it also is subducting all the way under North America. All of the topography you see in southern Alaska is a byproduct of this one collision event. Even Denali, which is the far field one. In fact, they can track the deformation all the way back into Canada. But it's this plate, microplate, that's slamming into North America that's causing the mountains to go up. And so what we're trying to do is, that's the mountain range that's got the glaciers on it, and it's eroding out. And we're trying to figure out what's happening to that mountain range. But at the same time, we're also interested in what's happening out here in the North Pacific. So it's made up of a fold and thrust belt that's sort of arranged in this geometry here. So that's the active part of the collision. And there's some other tectonics that are going on here as well, that where the faults come together that we'll talk about later. Alaska is really known for the glaciers. That's why you have all the cruise ships and everybody going there. Has anybody been to this part of Alaska? Okay. So if you have, then you know that there's ice everywhere. But there's also lots of sediment. And this is a satellite photograph taken on one of those cloud-free days in the Gulf, pretty rare, that shows the very large plumes of material that are coming off Alaska. And this whole area supplies the equivalent amount of sediment as the Mississippi-Missouri River system to the oceans. It's just huge. And it's really a byproduct of these very large glacial systems. So the Bering, Bagley, the Malaspina. The North American Yakutat fault zone is right in through here. It's right where the fault is. And so this is our study area, and this is what we're looking at is the Cordilleran ice sheet. So in North America, we have the Laurentide and the Cordilleran. This is the smaller of the two, but it's quite dynamic. And well, we're working with our folks at the University of Maine and their ice sheet model to look at exactly how this area changes over time. So this is their model. It's forced by sort of global climate, but just to give you some general feel for how their model is showing the Cordilleran behaving over a 100 kiloyear cycle. So it starts off in an interglacial, and you begin to see this. What I want you to get from it, it's just following global climate, but you get the sense of this pulsingness. The ice is moving through those mountains very rapidly, and it gets very large, and it's that dynamic state of ice that is what we're really keen in on here. Ultimately, we'd like to couple this with where the sediments are coming from to figure out exactly how accurate that model is. All right, so if you want to test any kind of concept here, there has to be some things you want to look for. And Kellen Whipple in his paper said, if climate really is changing mountains, these are the things you're going to want to look for. And so these are all a series of things we're studying in this area. I'm not going to get into these last bits here. That's part of the STEEP program. I'll come back to it and summarize what they found. But I'm going to primarily focus on the marine part of this one and what we found with the drilling program. So if you're familiar with the drilling program, I'm the chair for another 2 weeks of the U.S. Advisory Committee for Scientific Ocean Drilling. So if any of you in the room are interested in wanting to apply to SAIL, speak to me. If you can't find me, Amelia's on the same committee. So We were responsible for staffing U.S. participation in 3 different kinds of platforms: the Chikyu, which is Japanese vessel, the JOIDES Resolution, which is U.S., and then mission-specific platforms, which is what the European consortium is funding. So we use the JR, which is pretty much the workhorse for the drilling program. And to be quite honest, the JR has not had a great record for drilling in glaciated areas. It's really good for going out in the middle of the ocean into soft mud and poking holes, but not so good for places where you have icebergs. Because the technology that we use is one where the best cores come from you drill down and then you shoot a core into the formation in front of you. And you get, it's a piston core, so if anybody's ever seen a piston core, this is a hydraulically triggered one that's 9.5 meters long. Gets you wonderful quality core. If you can piston core it, it's great. If you can't, then you just start rotating the drill string and you just drill like any other kind of technology, and that stuff goes up in here. You can imagine that in an environment where you've got icebergs and ice rafted debris, if you have a boulder and you hit it with your piston core, it'll bounce. Or even if you're trying to drill, you hit a boulder and it'll just spin the boulder in place. So the folks that gave us the green light to drill this were really worried about what kind of recovery we'd get and whether or not we'd even be able to test our story. So again, just to kind of give you the overview of the drill sites, 1417 is in deep water, 18 is moving in deep water, but it's closer, and then these shelf sites here. So we drilled here first, and because we knew from the previous drilling from DSDP that it goes back into the Miocene. And we knew that it covered time periods that we were interested in, so it's a good place to start. We had some idea based on the previous drilling as well as some other work done in the Gulf of Alaska, a more distal site here, that there was probably a link between climate change and what we're seeing in the Gulf. So to work you through this here, here is the record at a distal site. What they noticed was about 2.5 million years ago, a major increase in the amount of ice rafted debris carried out there. But they'd seen evidence of some ice rafted debris earlier than that. At the same time, the IRD really begins to show up. You see an increase in the amount of sediment coming out there. You see another big kick about 1 million years ago, which is right about this mid-Pleistocene transition. What we also did, we published this in 2008, what we saw onshore actually was a change in the exhumation of the mountains themselves. They sped up about 1 million years ago. So we saw both onshore evidence that the mountains were moving rock up faster at 1 million years, but also offshore that the mass was going somewhere. But this is a distal record and we wanted to move closer. So big picture of what we're trying to do here. This is the